Hello everyone, welcome to this webinar. Today we'll be covering our power factor tool for pvDesign. And for now, we're gonna wait a few minutes for everyone to join. And in this time, I will show you some of the good pages that you can go to access all of our sources. So first of all, just to remind you that you have access to future webinars that we will be doing in the near future, covering quarterly update products or releases and every single topic that you could expect. And also all of these webinars will be available in our YouTube channel. So feel free to visit them. There's a lot of interesting topics. You can learn a lot from our colleagues. And that would be it for a small presentation for our webinars. And for now, again, let's just wait a couple of minutes for everyone to join, and we will be starting soon. Okay, I think we have time for everyone to connect. So welcome everyone. Today we will be talking about power factor, how power factor is calculated in our software pvDesign, how it's useful for PV developers, and why is it a necessary requirement when we are creating a new PV project, specifically with the grid status of right now. So without further ado, let's start. First of all, a little introduction of myself. My name's Álvaro Benito. I joined RatedPower around 2 years ago as a software developer and also as an electrical engineer. I've been working here in the interconnection team for features such as the AC coupled batteries, overhead lines, substation, and power flow model. And today we will be covering the power factor calculation that it has been live for a long time. So first of all, the index of the presentation, we will do a small introduction of what is the power factor, how can it be calculated, and some basic about it. Then we will jump into power factor in pvDesign, how do we calculate it, how it can be set by the user, how it can be used in general for our designs. Then we will move on to a chapter regarding capacitor banks, which is a new feature that will be available for users in the near future. Then we will jump into power flow calculations with the currently available power flow model. And finally, we will have some Q&A sessions for you to ask whichever questions that you have regarding the presentations or any other topic. So let's start with a small introduction. First of all, we need to know the definition of power factor. So power factor is the ratio between the real power and the apparent power that we have at the output of a system or at the input of a system. This can be shown with a small triangle in which the hypotenuse will be the apparent power, and then the straight line that you see below is the active power. This active power is the only power that is actually useful for our day-to-day tools. So our objective is to minimize the reactive power that we have and that we generate. And because of this, it's really important to keep the power factor calculations and power factor estimations of our PV plants accurate, because we will want to try to aim for this specific value of power factor equal to 1. So moving on to why is power factor important, because as we mentioned previously, it's important to keep it close to 1 so that all of our apparent power converts to active power. Currently, in all the systems that we have, such as power transformers, transmission lines, and virtually any device that we have at home, such as like motors, ventilators, typical devices that we use in our day-to-day lives, they are usually inductive loads. Inductive loads meaning that they absorb reactive power, so they kind of reduce the amount of active power that we have. So in order to compensate for these inductive loads, we have to compensate with capacitive compensation. We have different strategies for this capacitive compensation. The first one in PV plants is the usage of inverters. Inverters are electronic devices that can work under different conditions of active and reactive power, so they can allow us to work and to compensate these inductive loads. Then the other possibility is to have capacitor banks. Capacitor banks are basically a bunch of capacitors connected to the substation directly, and these capacitor banks will compensate the inductive loads that we find in our day-to-day elements. So just for you to understand why inverters can compensate for this reactive power, this is an inverter's curve obtained from a string inverter of Huawei. As you can see, it has a range of operation in the horizontal line from Q inductive in the left side to Q capacitive in the right side. So that's the amount of reactive energy that this inverter can absorb or inject to the network. So having this flexibility allows us to work and compensate whichever capacitive or inductive load that we have. And then the most important thing why we want to achieve this power factor, this capacitive compensation, is because we will have local grid requirements. So specific countries will force us to have a specific power factor at the end of our PV plant. So this is something that is going to be necessary and required. So typically values between 0.9 inductive and 0.9 capacitive are required by the governments. And in order to achieve this, we need to do some studies and to check how many inverters we put in our PV plant, etc. So having done this small presentation, first of all, for those who don't know what pvDesign is a software that automates the design of a PV plant. It also calculates the energy assessment of this PV plant. It calculates and sizes the substation equipment and the interconnection line from the substation to the point of interconnection. So within pvDesign, we have a power factor tool, and we're going to show you how to use this tool in the software for your specific PV project. And then before everything, just a quick reminder, you have available in our webpage a lot of methodologies. These methodologies are technical documents that cover all of the technical calculations, mathematical calculations, etc. And one of them is specifically for the power factor calculation. So everything that is covered in this chapter, you will be able to find it with more detail in this methodology. So just for you to know, all of this information will be sent to you by email after the webinar. So you will have access to every single piece of information. Now, moving on to how we calculate the power factor. First, let's review the PV plant elements. First, we have the inverters. We're gonna omit any elements before the inverters because they are not related to this specific part. So after the inverters, we will have low voltage AC cables, which will go to the power station transformers that will raise the voltage to medium voltage. Then from the power station transformers, we'll have MV cables going to the substation transformers. And then finally, an HVAC cable, which can be an overhead line or an underground line to the point of interconnection. So all of these systems generate inductive loads or resistive loads. So for example, I'm going to show you some of the electrical models that we have internally to size these systems. So for the low voltage AC cables that go from the string inverters to the power stations, we consider them as purely resistive losses. We can set the percentage of these losses in the software directly as a maximum voltage drop percentage. Then we can set the MV and HV cables again as well in the software. We decide a maximum voltage drop for each of them, for the MV system and for the overhead line. This voltage drop, we assume that is similar or equal to the power losses based on some assumptions. And for this case, for the MV lines, what we do is we estimate that we have an equivalent MV cable, which has a section of 400 square millimeters, typical sections of PV plants. And then based on this equivalent MV cable, we calculate or estimate rather a resistance and a reactance. And based on this resistance and reactance and the user input, we can calculate the resistive and the reactive losses. And for the HV cable, it's similar, same approach, but the section will depend on the capacity of the PV plant. This is the electrical cable, the electrical model that we use for the MV and HV cables. Very simple, a resistance and a reactance, and that's it. And then finally, moving on to the transformer's electrical model, we will have two types of losses. We will have copper losses and iron losses. The copper losses are load dependent. This means that when current is flowing through the transformer, these losses will increase because they are caused by Joule heating. And also these values tend to be higher than the iron losses. The iron losses, however, they do not depend on the load. They are always there as long as the transformer is magnetized, and they typically tend to get lower values. Both of these losses generate both active and reactive losses. So both are consuming active power and reactive power. And now the electrical model of this transformer is shown in this image. This is a normal image that I got from Google. It's a typical electrical equivalent model of a power transformer. And as you can see, we have copper losses, which are the green elements. So the green impedance at the primary winding of the transformer and the green impedance at the secondary winding. And then we have the iron losses, which are caused by this parallel branch, which is the magnetization current and magnetization branch of the transformer. As I mentioned, copper losses will depend on the load, and the other one, iron losses, will not depend on the load. Now let's go through a detailed calculation of a specific example of how we internally calculate the power factor that the user requires. So let's say we want to have a power factor at the output of the substation of 0.9. So we want to know what is going to be the power factor at the inverter level. So how we will want to operate our inverters in order to reach this power factor of 0.9 at the output of the substation. So the first thing that we're going to do is just guess. So we're going to take a first guess of the inverter's cosine of phi. In this case, I selected 0.814 because it fits with the drawing. And from this, we start subtracting the losses of the different systems that we have in the PV plant. So first, we go through the power station. We have some resistive losses, which is the horizontal line, and some reactive losses, which is the vertical line. Then we go to the MV cables, again, some resistive losses, some reactive losses, and then we go through the power transformer of the substation. And we end up with a cosine of phi of 0.968. This is not the target power factor, of course. We didn't reach the 0.9, so we kind of have to iterate again. We have to make a new guess of the inverter's power factor, and we will keep doing this in a smart way in order to achieve the result that we are looking for. And after some iterations, we end up with this graph right here, in which our final cosine of phi at the inverters is 0.7316, and our objective 0.9 at the substation is achieved. Now, this value right here, you might have issues if the design is not correct achieving this power factor, because the manufacturers might not be able to get you to this reactive compensation. So this will require you to rethink about the design of the project or to add additional compensations such as capacitor banks. And in this case, looking at the triangles that are generated, these are similar to the triangles that I mentioned at the beginning. So we will have the blue triangle for the power factor at the inverters and the green triangle for the power factor at the substation output. Now, I'm going to talk about some of the initiatives that we have in the team. First one is the capacitor banks. We're expecting this to appear in pvDesign in the following weeks and maybe 1 month at most. First of all, capacitor banks are just electrical elements that are these circular metallic pieces that apply reactive compensation. They inject reactive capacity into the grid, correcting the power factor. They are also used for stabilizing the voltage level in the PV plant and in the grid. And they are, due to them, we can reduce the number of inverters. You're going to see this clearly in the following chart. In the left side, you can see exactly the same image that you saw previously. We had a power factor at the inverters of 0.73. And if you look at the line that goes from the origin of the graph to the S of the inverter, this line right here, you will see that it's a long line, way longer than the one that you see in the right image. So this means that the apparent power of the inverters when we add capacitor banks is way lower. The capacitor banks in this case are the blue line, the blue vertical line in the right side. Due to that compensation, we can reduce the number of inverters required in the PV plant and maybe to reduce the cost of the PV plant, because if we add a capacitor banks, they are also costly. So we have to run some economical analysis here to find the cheapest solution and the most stable solution. So just a sneak peek on what capacitor banks will be in pvDesign. This is an image extracted from a single line diagram of a substation. You will see here a capacitor bank feeder on the left side with all of its protective elements, the disconnector, a reactor to avoid transient short circuit currents, etc. So you will be able to see this in future developments. So expect it in around a month, more or less, and you will be able to tweak and play with it. Now moving on to power flow calculations. Recently, we released a power flow model, and we will be talking about this later. But first, let's study why do we need these power flow or load flow calculations and what are they? So first of all, from what we have seen previously, we have a model to calculate the power factor. We have everything, but this model is not perfect. This model has some limitations. The first one is that it uses simplified electrical models. The electrical models that I showed are not exactly modeling the real behavior of the different elements. So they are simplified. They do not show the reality. We are not considering the voltage drop between systems. So we are considering that the voltage across every single element of the PV plant remains constant. And this is something that, depending on the accuracy that we want, might or might not be acceptable. And we are considering only one power transformer for a PV plant. So we have like an equivalent power transformer of the entire PV plant, which is not exactly correct. And this analysis is perfect for energy assessment. You will see in a minute that it works flawlessly. It doesn't really have that much error. But if we want to run a deep analysis on power flow, if we want to know the reactive and active power at each node, it's not enough for us. So this is where power flow model comes in handy. So a few months ago, we released this new feature, a power flow model. This is an equivalent electrical representation of the PV plant, of all of its elements. So here we will have, for example, an overhead line in the left side. This is an overhead line. Then I'm going from left to right. Then we will have power transformers. In this case, we have 2 power transformers in our substation. And then from that, we have what are called MV collectors. MV collectors are basically like equivalents of the MV lines of the system. Then we have the power station transformers, again, equivalent systems. They are a collection of a bunch of power stations. And finally, we have the equivalent generators. So with this electrical equivalent system, which is, by the way, based on the Western Electrical Council of the US, we can have a more accurate equivalent electrical system, and then we can run load flow calculations on this electrical model. Now, load flow calculations will provide us with this information at every node. We will have the voltage level, the voltage phasor. So this means that we are going to be considering voltage drop between systems. And then we will have active power and reactive power at every node. So we will have we will be able to calculate the power factor at every node and the active and reactive power, which is all of them are kind of related to each other. And then I'm not going to go deep into the maths behind it, but we are working on a methodology based on the Newton-Raphson method, where this calculation model is being used in most softwares of load flow calculations, such as Dixilent, ETAP, or PSSE. We will also work in the same way as we are working right now. So we will start trying to guess the power factor at the inverters that we want and try to reach, again, the 0.9, for example, at the output of the substation. And we will provide with the power factor at each equivalent inverter so that you know more specific calculations and more in detail with a more accurate model, all of the results that you want. And this will be available in the future of pvDesign. I'm not going to say any specific dates because we are uncertain about this, but we are working on it right now. And now let's jump into pvDesign to show you a little bit how this tool works. Okay, so we have pvDesign open right here. Let's go into this power factor webinar project. And I'm going to start a new project from scratch. Okay, so this is the main page of pvDesign. We have a site with a substation right here, a battery area because we allow for AC coupled BESS, and 2 available areas, and finally a transmission line. So if you go to the grid tab and to the grid requirements section, we have here a part which is sizing using power factor requirements, cosine of phi. So if we enable this option, our PV plant will be automatically calculated and sized, trying to respect some of the power factor requirements that you need. So first of all, we have to define the delivery point. This is the point where we want the desired power factor. So typically, we will want it either at the substation input or the substation output. Let's say in this case, we want it at the substation output. And our grid requirements say that we need a power factor of 0.9 there. So our tool will automatically estimate what power factor we need at the inverter's output. Now, let's say we haven't set our losses, for example, we haven't set our equipment. So if we change our inverters from central inverters to string inverters, we will see that this grid requirements, this power factor change from 0.82 to 0.8347. This is because we included string LVAC cables. So these were not included in the previous system, but with string inverters, we have them now. Then if, let's say, we have to set the different losses, so instead of 4.5%, we have like a 2.5% losses in the LVAC cables. In the MV system, let's say we have a 0.3% losses of the MV cables, and we will see that this affects the power factor at the inverters. So all of these values are related to the electrical models that we saw previously. Now we can run this design, and instead of waiting, since I already ran specifically this simulation, I'm going to go back here, and I'm going to download some of the documents. Specifically, you can see in the energy yield report that we generate. Well, first of all, for those who haven't used pvDesign, we will generate a lot of documentation, documents, spreadsheets, and drawing, whenever you run a simulation. So you will be able to access to every single one of them. And one of them is the energy yield report. So let's go and download this. Okay. So we have it here. And then we can access to it. And there's a lot of information, a solar resource, PV plant, etc. But we're going to focus on what's important for us in this webinar. It's chapter 7 in the energy yield results. We will expect to have a power factor at the substation output of 0.9, which is the one that we wanted to get. So after running the energetic model, we reach a power factor of 0.899. This small error is due to the fact that we are having some assumptions at the stage where the inputs are selected. But as we can see, the result is almost equal, and we reached a good and accurate result. And we can say that that power factor at the inverters makes sense. Again, we can see I'm just going to show you the power flow model because I think this is really interesting for it. So this is again generated automatically by pvDesign. This is the equivalent system. As you can see, it's slightly different. We have 3 battery generators. It's because it's not a realistic PV plant. It has a lot of batteries and not that many PV. But using this model right now, you can feed all of these values to your own calculation models or other softwares. And from them, you can then run their load flow analysis or any type of calculations that we want. We will provide with the resistances, reactances, per unit values, everything. So all of this information will be enough for you to run any simulation in other tools or internal tools. And that's it for pvDesign. So thank you all. I'm going to jump now into the Q&A session. So if you have any questions that you want to ask, just feel free to put them in the chat or ask them, and I will start answering some of them. Okay, so one question is, will we be able to manually size the capacitor banks in pvDesign? Yeah, so right now we are gonna give the option to decide which equivalent systems of the software will be compensated by the capacitor banks. So you will be able to say, for example, I want the power transformers to be compensated by the capacitor banks and the MV lines, but then the power stations, I want them to be compensated by the inverters. And you can play around with the tool to kind of establish a bit of the configuration for reactive compensation that you want. Okay, so I'm seeing in some places there's a requirement of a power factor of 1 at the point of connection at the grid company. This might require a reactor compensation at higher voltage. Yeah, for now, we are only providing capacitor banks as the only option for compensation. Also, if there's any other strategies, we will think about them. Yeah, there's like millions of possibilities. There are static var compensators, there are reactor compensators, there's a lot of options. For now, we opted for capacitor banks because they are the most typical used apart from inverters. And that's like the secondary option that we are applying right now. Okay, let's wait a bit for anyone to ask any possible questions. Okay, just a reminder, we will send you all the information regarding the webinar. You will have access to the video online in our YouTube channel. So every single resource that you want, just feel free to contact us if it's not enough with what you present us. And if you have any questions, feel free to contact us via email. Any of us will be happy to help you out and to answer any question that you have. And I don't see any more questions, so I think we can close it here. Thank you all for coming. Thank you all for attending, and enjoy the rest of the